Good evening. Can you hear me?
Yes, sir.
Yes, sir.
Okay. So yeah. So what we will do today is the following. So I just so the agenda will be the following. So we will start with describing a feed-forward network, right? So that is what we are going to look at today. So feed-forward network, what is it? So this is all summary, okay? So feed-forward network, and we will look at what is the forward pass. So the forward pass equations and the backward pass equations, right? So the back propagation, as we call it. So these are the three things we'll be doing today. So, okay, week 3, right? We are in week 3. Week 3 deadline is Sunday. Is that correct? Okay, yeah. So what we'll do, so what I'll do is I'll just keep going, and you can interrupt me if something is not clear. I am hoping that the forward pass will be quite easy. So there's nothing complicated in that. The backward pass might be slightly difficult, right? So it depends on how you have tried to understand that part. So that might be a bit tricky. So we'll see how to work with that. And we just uh, increase the font size. It's good enough, but maybe we can make it a little bigger. Okay. Yeah. So first is a feed-forward network, right? So that is what we are going to look at first. And this is a very convenient tool that is available online to just visualize networks with different number of layers, right? Okay. So you have, so I'll go over this part quickly because you all already should be aware of what a feed-forward network is. So input comes in here on the left-hand side. So in this case, input is in R5, right? So there are 5 features. You can think of it as features. And we call each of these neurons, right? These are the input neurons. So there are 5 input neurons. And then you have a bunch of hidden layers and then one output layer, right? So that's what makes up a network. It's called feed forward because the connections are always from left to right. They always move forward. So you can actually draw the, can show the direction of the edge. I think it is there somewhere. Show arrowheads. So if you notice, these arrowheads are pointing from left to right. Okay, so that's what makes this feed forward. The distinction is important because later on we'll be looking at networks which have connections that form. So we'll have loops forming, right? So these are called recurrent neural networks, where there is a connection from one neuron to another neuron across time steps, right? So we'll be looking at such networks. So to distinguish between them, you have what is called a feed-forward network, okay? So in terms of graph theory, can someone tell me what kind of a graph this is? This is a special kind of a graph. Does anyone know the name of this graph?
Connected graph.
Well, strictly speaking, it is not connected, right? Because if I am in this node, I can't reach this node. So it's not connected,
Yeah, right.
right? So it's a directed graph, but it's a special kind of directed graph, right? So it's
Yes,
what?
so it's acyclic.
Yeah. So it's a directed acyclic graph, right? This is called a DAG. So it's not important, but then it's good to know. So this is directed, and it's acyclic. There are no cycles involved. So that's another way of looking at it. So what we'll now do is we'll take something that will fit nicely within the scope of our screen. So I will make the number of neurons here, say 4, and maybe I'll turn this into 3. And then the number of outputs will be 2. Okay. So I'll quickly move this to another page. For now, this is the layer spacing. I think this much is enough. Okay. What else do we need? I'll remove the arrows. I think that point is clear enough, right? So you don't need the arrows any longer. node diameter, maybe that much is enough. Okay, so I'll take a copy of this, and then we'll move on to the other page. Okay. Okay, so this is a typical feed-forward neural network with how many layers are there? So these are conventions that you should get used to. So how many layers does this network have?
4.
2.
Okay, so this has 3 layers, right? So the convention that we are going to follow is there is going to be an input layer. Okay, there are 2 hidden layers. Okay, so 2 hidden layers and 1 output layer. So we are not going to count the input as one of the layers. Okay, so that's not going to be one of the layers. So we will call it layer 0. Just to be clear, we will call this layer 0. And we'll call the 2 hidden layers layer 1, layer 2. In fact, wait, what is the convention that the prof follows? He follows, that is correct. Yeah. So, and the output layer is the third layer, right? So there are L layers. So 3 layers. This is, so layer 1 and layer 2 will be the hidden layers, and the output layer will be layer 3. So can someone confirm if this is what the prof follows? I don't know if the lectures follow this exact convention.
Yes, it
Okay.
is layer 1, layer 2, and output layer is termed as either layer 3 or layer N.
Okay, layer L. Okay, so there are yeah. So in general, there are L layers. Okay, so and layer 0 will be the input, and layers 1. So layer 1 to layer L minus 1, right? So there are L minus 1 hidden layers. So these will be hidden layers, and layer L will be the output. Okay, so this is the idea. So I hope all these things are clear to you. Okay, so nothing new I'm telling here. So this is the convention that we are following, right? Some others follow other conventions, right? So they might call this a 4-layer network. It's just a matter of convention. Okay, but we are choosing to call this a 3-layer network. Now, what else should you know? You should know that there are 2 main classes of problems, right? So there is classification and regression, right? So depending on the problem, the number of outputs in your layer will change. So typically, if you are solving so this is the output layer, to be specific. So if you are solving a classification problem, how many nodes will your output layer have? So nodes or neurons, right? We are going to call these neurons. So how many neurons will it have?
2, or depends on the number of classifications
Classes,
given.
right? So it will have that as many neurons as there are classes. We'll have, let's say, C neurons, right? So I'm going to call it, it's a multi-class classification problem. Apologize. Just give me 1 minute. Apologies for that. So there are, where were we? So we were here, right? So this is a multi-class classification problem with C classes, okay? And then that will determine the number of outputs you have. So output layer will have C neurons, okay? In this case, this is a binary classification problem, and it has 2 classes. So there is an alternative. So if it's a binary classification problem, you can also do it with just 1 neuron, but then we'll come to that later, right? For now, let's not get that into the way. So if it's a classification problem with C classes, your output layer should have C neurons. Okay, so that is there, and if it's a regression problem where you have only one regression output, typically you have only one output, so that's a scalar output, so that will have just one neuron. Okay, I hope this part is clear. So this is the general idea behind the feed-forward neural network. Now, any questions so far regarding this, the feed-forward neural network as such, what it's trying to do? Okay.
Sir,
Yeah.
sir, could you please explain the classification part?
So if there are, see, there are here how many classes? 2 classes, right?
Yes, sir.
If there are 2 classes, you will have 2 nodes. So if you have, let's say, 3 classes, then you will have 3 nodes. For instance, this is, you are trying to predict if a given document, let's say you have a text document, and you have to predict if it's a spam or not spam. Okay, that will be the binary. So let's say sentiment analysis, right? So you are trying to predict the sentiment of a piece of text. So the sentiment could be positive, it could be negative, it could be neutral, right? So depending on what that sentiment is, you will either this neuron will fire, or this neuron will fire, or this neuron will fire. Okay, so I mean, all 3 will fire in some sense, but they will represent the probabilities associated with these 3 classes. Is that clear?
Okay, sir.
It's a new feature that I'm seeing. I actually wanted this feature. How did this work? If I double click it, something got highlighted. Anyway, we'll come to that soon. Okay, so I think that part is clear, right? So we can now move on to the equations. Is that fine? Forward pass, as we call it.
So what about the weights? Could you explain that?
Yeah, we'll come to that. So that's where the forward pass will come in. So for that, what I need to do is I need to copy this and place it here. 1 second. We need to copy this. Okay, this is.
So I have a very trivial question.
Yeah.
The last layer, the one which we call output layer, are
Yeah.
those neurons actually that layer processes the output, or it is actually the output itself? That layer will give the output then. It's a
Yeah.
final layer.
We will come to that. Yeah, when we are discussing the equations, I'll discuss that also.
Okay.
I think it calculates the loss function and then give the output.
Yeah. So every neuron is a computational unit. So meaning at every neuron, some computation happens. Maybe we'll do that first, right? So let's do a single neuron. So what happens at a single neuron, right? So this is true for every. What is spelling of neuron? Neuron is spelling, right? Okay. So this is a single neuron. Let me see. I'm going to take some time to draw. Okay, I have not prepared slides, so I'll have to sit down and draw some of these things. You'll have to bear with me. Okay, so this is a neuron. Okay, so this is a neuron. This is let's call this input neuron. So these are 3 neurons which will be sending us inputs, and let's look at what happens to the inputs as they get processed at this neuron. Okay, I'm going to call this neuron the output neuron, right? This is where the processing is going to happen. Okay, so you can think of this as, say, these 3 neurons, and I'm focusing on this first neuron in this second hidden layer. Okay, so you can think of it that way. Actually, I should have 4, but for convenience, I'm just having 3. So the convention is the neuron that is sending inputs to the next layer, right? So the inputs are going to be called H. Okay, so I'm going to call this H1. Okay, and this is going to be H2, and this is going to be H3. right? So these are, if you think about it, H1, H2, H3 are the outputs of these three neurons respectively. Okay, and they happen to be the input of the neuron in the next layer. So the output of a neuron in layer L will be the input to a neuron in layer L+1. I hope you see that. Okay, so that's the main idea. So H1, H2, H3 are the inputs. So what is this neuron going to do? This neuron is going to take these inputs, okay, and then do something with it. So there is, as you can see, a connection between these two neurons, and every connection is going to have a weight or a strength. Okay, so we can, for simplicity, we just call it W1, W2, W3, right? So this is W1, this is W2, W3. Okay, so if these are the weights or the strengths of the connections between neurons across two levels, then how is the computation going to happen? Can someone tell me what will be the output of this neuron? It will be W1, H1. So input is H1. How important is this input? It is as important as W1 into this, right? So that's the effective importance of the input coming into this neuron from the previous layer's first neuron. Okay, so this is W1, H1. Similarly, plus W2, H2 plus W3, H3, right? So this is the linear combination, as we call it, of the inputs coming from the previous layer. Okay, so is that all? So is this the output of this neuron? It is not. So we are missing out on what is called the bias, right? So every neuron is given what is called a bias term. So the bias, what it does is it gives you a sense of how likely the neuron is going to fire, right? So it is the, so bias is a neuron's what is the spelling? Predisposition. Okay, I don't know if I have spelled it correctly. What is the spell check? Okay, so this is the neuron's predisposition to fire, right? So meaning if H1, H2, H3 is all 0, how likely is it that the neuron's output will be some positive value, and that is B. So did you all get what I meant by a neuron's predisposition to fire? I hope you got it. Okay, so this quantity is what is called A. Okay, so A is this quantity, and we give it a name. We call it pre-activation. Okay, so that is called pre-activation. And what happens to this A? It is passed through what is called an activation function to give you H. So your neuron is actually going to output H, a new H here. So that will be the neuron's output. And just before it becomes H, what will happen? It would have computed A. So let me add that here. So somewhere just before the neuron, you will represent this as A, and then an activation function will be applied, which will turn the A to H. So this is the activation. Okay, so any questions regarding this part? Does everyone get?
Yeah, regarding this A pre-activation, can we say that pre-activation is a function or is it a variable?
Pre-activation is
Because we are taking all the parameters and just combining it, right? We are returning something. So is it a function or is it just a variable?
it's just a variable, right? You don't necessarily treat it as a function. It's the pre-activation is just the linear
Okay.
combination of the activations from the previous layer. Okay, so
Okay.
and the activation function is going to convert the pre-activation into an activation.
Okay, got it, sir. Thanks.
Okay, so typical activation functions include the following. So you have seen sigmoid. So sigmoid is a very common function. So this is g of z equal to 1 by 1 plus e power minus z, right? So that is one. Then you have tan h. I don't remember the formula for tan h. Again, some function of e power z, e power minus z. Okay, so you can refer that. But by far the most popular of all is what is called ReLU, right? So ReLU, I don't know if you have introduced, but very soon you'll. So this is nothing but the maximum of 0 comma z. So if z is a negative value or z is a negative value, it will be 0. If z is a positive value, it will be z itself. Okay, so these are some activation functions. So you'll see why activation functions are needed. But before that, does anyone already know why activation functions are needed? Why are activation functions important? Does anyone know the answer to that? Yeah, to introduce non-linearity, right? So if you have no activation functions, what your network will be doing is it will be computing a linear function of the inputs, right? So if there is no activation function, right? So, or rather I put it this way, if the activation function is not linear, the network will end up computing a linear function of the inputs. And this is kind of useless, right? Because you already have linear classifiers, so such as logistic regression, SVM, right? And why would you again want to present a linear classifier in the form of a neural network, right? That's a waste of computational effort, right? So you need non-linearities, and for that you need to have non-linear activation functions. Okay, so you can actually think of a neuron as doing two things. It's doing a linear combination of inputs from the previous layer and then adding a non-linearity on top of it. Okay, so there are two aspects to a neuron. So you have to, this is very important. So the pre-activation is the linear combination. The activation is what makes this non-linear. Okay, so is that clear? Can we move on to more than one neuron in a layer? Okay, so I hope that's fine. So we have to now start looking at multiple neurons in a layer. So we will take the same image. This is so far one neuron. Now we can.
Sir,
Uh,
above three
yeah,
functions are nonlinear functions.
yeah, all three are nonlinear.
What is vanishing gradient problem?
Vanishing gradient problem, we'll come to that. So it is, it
These
happens when you have.
three functions all are related to saturation.
That is no, not all three. First two are related to, so first two will saturate, but ReLU will not saturate. So you have another kind of problem associated with ReLU, which is called a dead neuron. But we will, for now, let's not worry about that. Okay, so the vanishing gradient problem, let's not concern ourselves with it. Now we are only trying to understand very basic ideas associated with a neural network.
Okay, sir.
Okay, so now what we'll do is we will get rid of this and add maybe just one more neuron and add these connections also. Okay, so how many connections do you have in total?
Six.
Yeah, you have 6, right? So in general, if you have, say, n, I'm going to use this terminology, it's very important. So if you have ni neurons in layer I, okay, in general, that's the terminology or notation we'll be using. Ni is the number of neurons in layer I, okay. So this will be, maybe this is layer 2. So this is n2. So n2 is in this case 3 and n3 is 2. Okay, so yeah, so if you want to compute the output here, you could do this, you could represent it this way, W. So you will have now, say W, you'll have to give this extra, you'll have to bring in an extra notation, right? So earlier it was just W1, W2, W3, but now there is going to be W11, W12, so on, right? And therefore, what kind of an object? So here it was a vector, right? So W1, W2, W3, you can add the weights into a vector, and that vector would be of this form, right? So it will be W1, W2, W3. If you're just looking at one neuron, but if you have multiple neurons across two layers, what will this quantity become?
Matrices.
Matrix.
Yeah, it will become a matrix, right? So now, what will be the size of the matrix that I represent here? So
2 cross 3.
okay, right? So here is an important point. So again, this is convention. We will always follow this convention for the weight matrix, right? So what is that convention? We will have, in terms of text, right, and not symbols, it's the output, or let's say, yeah, output layer cross input layer. Okay, so you should always tell the output dimension first and then the input dimension. So it will be 2 cross 3 in this case. And therefore, each row, okay, each row of the weight matrix corresponds to one neuron in the output. So it will become clear if I, this is 2 cross 3, right? So this is how it looks like. Now this is, the first row corresponds to this neuron. We will make this explicit. So the first looks a bit ugly, right? If I draw this arrow, I hope you understand, right? So there are only two rows, and they are associated with these two neurons. So this will be W11, this will be W12, this will be W13. So what are these? This is W11, and I'll maybe draw it as two separate figures, right? So this is, let's get rid of these things. This is W12, and this is W13, right? So that is the first row of the matrix, right? So first row of the matrix corresponds to the first output neuron. Likewise, the second row of the matrix, so that would be what? W21. So that is W21. I'm not going to write down that here, okay? Because that's going to take, that will be too very cluttered. So that's W22, that is this one. And then there is W23, right? So that is W23. So W23 will go from, okay, so is this part clear? The first row corresponds to the first output neuron, second row corresponds to the second output neuron. So the rows will give you all connections leading into some output neuron. Likewise, the columns, right? Columns will give you all connections going out of an input neuron. For instance, if you look at W11 and W21, so W11 is this, okay, W21 will be this one. So the columns will give you these connections, okay, this ones. The rows will give you all the connections that lead to the input, that lead to the output neuron. So is this part clear? What are the rows and what are the columns of the weight matrix? Okay, so this is going to be useful later on. All right, so once you have this, notice that the equation, can I add the equation here itself? I think I have space, so I'll maybe add it here. So that is the weights, right? You also have biases. So every neuron has a bias except the input neuron. This is an important point, right? So here we had a bias. Now, except the input neuron, every neuron in your network will have a bias. So in this case, let's call it B1 and B2. Okay, and therefore this bias is a vector. So the bias is a vector. So this is B1, B2. Right now, notice what happens. You now need to find the output at this first neuron, and the output is nothing but the following. What is it? It is, to put it very simply, WH plus. So what did we have before? We had W sigma WI HI plus B, right? I could have actually written this as, so we can write this down as following, right? We could have written this as, in terms of vector notation, W transpose H plus B, right? We all agree that we could have written this as W transpose H plus B. Okay. Now, extending this idea, we can write this A as A equal to WH plus B. So the transpose is implicitly happening, right? So remember matrix multiplication, right? So this is W, this is B. I'll also add H for your reference. So H will be what? H1, H1, H2 or H1, H2, H3? How many units, how many components will it have?
H1, H2.
That's all.
That's all, sir.
So what?
H3 also.
Yeah, so
Because
H3.
we multiply with the W, right?
Yeah, not just because of that. The reason it has 3 is because you have 3 neurons in the input, right? So H1, H2, H3. So that's where it's coming from. So you have H1, you have H2, and you have H3, right? So okay, so that's where your input is coming from, right? So if this is not clear, notice what WH is. WH is nothing but this matrix. Okay, this is A is nothing but so how many A components are there for A? A1, A2 or A1, A2, A3?
Only A1 and A2.
Yeah, only A1 and A2, right? So remember, A corresponds to the computation happening here, right? The pre-activation. So A is this H1, H2, H3 plus B1, B2, right? So now this should be clear to you, right? So notice what's happening for computing A1. We are taking, let me make this so that this is, I don't want this disturbing the flow, so let's make it gray. Okay, so now notice what is happening. W11, W12, W13, that is the first row. W11, 12, 13. You are taking a dot product essentially, right? So W11 H1 plus W12 H2 plus W13 H3. That's the linear combination. Plus B1 is A1, right? Likewise, the other 3 weights which are grayed out, right? So those 3 weights you will multiply with H1, H2, H3 and add B2. So that will be A1, A2, right? So that will be A2. So once you have A, what remains? Now this is a new H. Okay, you should not confuse it with this H. Okay, I hope that part is clear. So this will be G of, I'll call this G of A, which is what? Which is again done element wise, right? So what is this exactly? This is H1, H2 again. So there are, always remember that the dimension of A and dimension of H is the same, okay, in a given layer. So this is H1, H2. This is applied element wise, meaning this is G of A1, G of A2. So if this is confusing, let me call this H prime. This is H prime. It refers to the next layer. Okay, so that is the feed forward equation for one layer from connecting one layer to the other. So is this fine with everyone so far?
Yes, sir.
Sir,
Okay.
sir, could you explain that H prime part? Like, how did it?
See, you have A1, A2, right? Did you get till that A1 and A2?
Yes, sir.
So you are getting some value A1 here and getting some value A2 here. So that is not yet the output. So these are still what are called the pre-activations. Okay, so A1, A2 is a pre-activation vector. What you finally need as output from the neuron is H1 and H2, right? So that is, you can represent that as H1 prime, H2 prime. So this is the final neuronal output. Okay, so output is going to come here. Likewise, so what we are interested in is H1 prime and H2 prime. So how do you compute H1 prime? G of A1. That is how you compute H1 prime. And G of A2 will give you H2 prime. So what is G? So G is one of these functions, right? So G of, for instance, if G of, if A1 ends up being, so if A1 ends up being say 0.5, then H1 prime, right, will be 1 by 1 plus e power minus 0.5. That is what H1 will be. Right? This will be the output of the neuron. Is that fine now with everyone?
Yes, sir.
Okay. So this is
Sir, this output is a scalar then.
output is each of these is a scalar, but if you
Oh.
put them together, it's a vector.
Okay, okay.
Okay. So now that is what we are going to come to. We'll discuss shapes. Shapes are very important. Now we are ready to generalize. So shapes of objects, right? So there are different objects. I'll just call them objects for want of a better name. So there are everything about forward and backward pass you can understand very easily, or at least remember easily if you track the shapes of objects that go through the network. So we'll copy this and paste it here. Okay, the input, maybe a table is better. So the input, or what is the object we are studying, right? So we are studying the input, and this is the shape. Okay, so this is nature of the object. So that's what we are looking at. So the input is the object, and that's a vector. Okay, so this, maybe you should interchange this and shape, right? So they are, so the nature of the object here is a vector. Okay, the input is always a vector, and it's going to have, I'm going to call this N0, right? So there are N0 neurons in the input layer. So N0, comma, right? So this is a tuple. So just to be consistent with Python notation, this is a vector, right? So vectors have only one dimension. So I'm going to call this N0. Now the first hidden layer is going to be again a vector. So what is a vector here? So the hidden layer one, so active, I'll call this the pre-activation of the, so are we calling it pre-activation? Yeah, okay. So pre-activation of the first hidden layer. So the notation for this is A1. Okay, so we are going to call this A1, the value that is just before it becomes activation, right? So that's A1. That's also a vector. What will be the shape of this? It will be N. It will be N1. Okay, so let me know if this is not clear. So this is, how do I move to the next row? So what is the activation of the first hidden layer called? Notation?
H1.
This is H1. Okay, this is also a vector. So this is going to be, shape is going to be N2, correct? Yes or no? How many of you think it's N2?
A1, H1 sizes both are same, right?
Correct. Okay, so this is N1. Okay, this is N1. So both are N1, right? So if in case it's not clear enough, this is N0. This is N0. There are N0 neurons, and then you have N1, okay, N2, so on. In terms of L, what will this be? This will be N.
L.
This will be NL, right? So there are NL neurons. Now these are all vectors. So this is the, I'll just call this the ith hidden layer. So that will change this to AI. Okay, activation of the ith hidden layer will become HI. Okay, so first hidden layer is A1, H1. So where are A1 and H1? That is also important to know. This is A1. So A1 is just before the neuron's output. Okay, that is the pre-activation. H1 is just after the neuron's output, right? So that output of the neuron is H1. In general, yeah. So one other point. What is this going to be called? The output of the input neurons.
H0.
That's going to be called H0, right? So, and what is the output of the neural network itself?
HL.
That will be HL, right? So the output neuron is also a neuron, right? Like all other neurons. So computation is going to happen at the output neuron also. So this is going to be called AL, and this is going to be called HL. The only difference is what activation function is used at the output layer. So that we'll come to that. Here, for all these hidden layer neurons, we typically use sigmoid, okay? Sigmoid or ReLU. But for the output neuron, depending on the task, we will either use linear activation function or the softmax function. Okay, so we'll get to that soon. So these are the shapes of the important vectors in the forward pass. Now we'll come to the weight matrices. So the weight matrix connecting layer I-1 and layer I. Okay, this is going to be a matrix, right? And what will be the size of this?
I.
Output neurons times
Correct. So Ni comma Ni
N
minus 1.
-1.
Ni minus 1.
Okay, this is N. So this, for instance, this will be N2 comma N1. So this will be N1 comma N0. Okay, this we can make this. Okay, it's ugly. So let's go back to N1 and N0 itself. I'll move it here just so that. So this, all these lines that you see, right? There are actually N1 into N0 lines. So all those connections, the values or the importance of those connections, they can be put into a matrix, and that matrix will have shape N1 cross N0. Likewise, this will be N2 cross N1. Okay. So we'll call this matrix W1. All right, we'll call this W2. Remember that the subscript is going to represent the layer on the right. Okay, so this is layer 1, right? So W1 will correspond to the connections from layer 0 to layer 1. Likewise, W2 will be layer 1 to layer 2. So whichever layer is momentarily called is the output for you, that is the subscript that will go here. Is that part clear to everyone? So if you keep doing this, the final layer will be WL. So that's okay. So in a neural network, in a feedforward network with L layers, we have so what will be the answer here? What will you fill here?
L.
Yes, this is the L, right? So you have L weight matrices. Okay, so there are L. You forget input, but then there are L computational layers. In some sense, each of these L layers, some computation is happening, right? Here, some computation will happen. Here, it will happen. Or the output also it will happen. So these are the number of weight matrices. Now, what is the other parameter that we have missed out? Bias, right? So
Bias.
bias for neurons in the ith layer, right? So this is a vector, and we are going to call this. So what will be the shape of this for the ith layer? Ith layer. So first layer, second layer,
Ni minus 1?
A1.
ni, right? Because you have as many.
Oh, yeah. Right. Yeah,
N1.
Ni, right? So this is ni. So these are the objects that are needed for us to compute the forward pass. So you have the input, and then the output is kind of one of the. It's nothing but the activation of the health layer, right? So two things that we'll have to note down. So first thing is L layer. So L layers we have L weight matrices and L bias vectors. Okay, so that makes it. You can actually give a gentle formula, right? So using this, the total number of. Don't mug up this formula. I think you should know this. Know how to get this. Is given by the following. You can actually write this down, right? So what will this be? It will be n1 into n0. That's the number of connections in the first layer. In the second layer, you have n2 into n1. That many weights are there. So it is n subscript something into n subscript something else. What will that be?
NL minus 1.
Yeah, so you have NL neurons in the output, and penultimate layer you have NL minus 1. So these are the number of weights. Okay, so I'll just add one more point. So the parameters of a network are its weights and bias, right? Both of them put together, we call them parameters. Okay, so these are the number of weights. How many biases do we have?
Number of neurons per layer.
Correct. Number of neurons per layer except the input layer, right? So you should not. So the input layer does not have any any bias. Though they are called input neurons, they don't participate in the computational effort. There's no computational effort there. They are only passing on inputs to the next layer, right? So wherever a computation is happening, that's where you need a bias. So in all layers, including the output, you have some computation. Okay, so therefore you have n1 plus n2 all the way till NL. So these are the number of neurons, number of biases. Okay, so is this clear? So this is like a number of params equal to this like important equation. Okay, please don't memorize this, but I hope this part is fine. Okay, so that is the shapes. So these shapes are very important because they help us in the backward pass. And yeah, so now for the loss function, right?
So I have a doubt, sir. Like these biases, are they only in the input layer, or can they be in the intermediate layers also?
No, bias is not there in the input layer at all. In every other layer, you have a bias for a neuron.
Oh, okay, sir.
Okay, so where is this? There is one full screen option, right? Where is the full screen here? Is this the full screen? Okay, that's better. Okay, right. So now we'll have to discuss two things together. So that is the loss function and the activation function at the output, right? So this output is a bit tricky. So we'll have to discuss both of them together. So we'll first discuss this for regression, right? So for regression, as we already mentioned, the output is a scalar, right? Therefore, there is one output neuron. The activation function at the output is called we call it linear, but what exactly is linear here? It's what is linear, by the way? So if
Identity.
it's just the identity, right? So actually, a better term is, somehow we end up calling it linear, but a better term would be identity. Okay, it takes the input and does nothing to the input. So why should this be identity for a regression problem? What happens if it is, say, sigmoid? Why can't it be a sigmoid? So why can't what is wrong if it is a sigmoid? Output would be between 0 and 1. That's right? So you don't want that. So nothing forces the output to be between 0 and 1. It could be any real number, right? So it should not be sigmoid. It should be linear or identity. Okay. So the first thing we have taken care of. So the output is, so how will it look like? It will look like this. If you just focus on the output layer alone, okay. So you delete the whole thing here and focus on this part alone. All the weights, all of them go away, right? Bias is still there. The weights are also there. I'm not saying they are not there, but so this is how the output layer will look like, okay, for a regression problem. This is the output. This is the penultimate layer, okay. So what will be the loss function? Sorry?
Mean squared error.
Yeah, that's, yeah, the mean square error. So yeah. So for convenience, we added half here. But what is this? This is exactly this, right? So it's y hat minus y the whole square. Half is for convenience, mathematical convenience. So y is the true label, y hat is the predicted label. Now these things are maybe confusing sometimes. So the output of the network is actually y hat. We call it y hat. But what is y hat? In terms of h something. What is y hat? It's actually
HL.
H capital L, correct, right? That's good. So y hat is HL. Please remember this. We'll use it interchangeably. Okay. So the network takes x as input and outputs y hat, right? So now, yeah, so there's some noise coming from somewhere. So in case you're not speaking, please unmute while you're speaking, okay? So this is what happens. So you can view the network as a function from R n0, okay? N0 is the number of features to R, okay? This is your regression network. And it does the following. It takes X as input and it gives you Y hat or Y. What is the output of the network?
Y hat.
Correct, Y hat, okay? Y hat is the output. Please note that. So Y is the true label. So the network takes X as input and outputs Y hat. The true label is Y, okay? And the network is actually a function. That's what it's doing. So this is what it does. The input is also represented as H. Input is what? H
H0.
H0, okay? So this is important. Okay, this is kind of confusing, but also important. So there are two things that we set. H0, we mentioned this somewhere, right? H0 is the input, that is X. HL is the output. That is also the same as y hat. Okay, I hope that this part is clear. So H0 is the input, that is x. Output is y hat or HL. Okay, HL is the output, but we call it y hat. And then this is the loss. Okay, so that is for regression. Now for classification. So for classification, what is it? The output is a vector. So maybe we can add the label is a scalar, right? The label itself is a scalar, the true label. Okay, so here the true label is a vector. Okay, in fact, we represent it as a one hot vector, right?
9 o'clock, 9 o'clock.
So what is a one hot vector? For instance, if there are 3 classes, then class 1 is represented as the vector. What is the vector?
1 0 0.
Correct, right? So class 1, class 2 will be likewise 0 1 0, and class 3 is 0 0 1, right? You have come across this in MLP, I believe. So one hot vectors. Okay, so the output is output also therefore has to be a vector, but it's something more. Is it any vector?
Probability.
Yeah, it's actually a probability distribution, right? So it's a probability distribution. So the y hat is it looks something like say 0.2, 0.3, 0.5, 0.2, something like this, right? For example, that's example. So if you want to make it very precise, if there are how many classes? There are capital C classes, and if you sum up y hat I, what will you get?
1.
1, right? So if you get 1. So the output is actually a vector, but not just any vector, it's a probability distribution, right? So, and therefore, you can actually start thinking of the loss function as something that compares to probability distributions. So the loss function is called cross entropy. So it's to be strict, it's categorical. You can call it categorical cross entropy, but it's just cross entropy, right? So remember that entropy is minus p log p, right? Minus 1 minus p log 1 minus p. Now, cross entropy is when you have 2 distributions. There you had only one distribution, p, 1 minus p. Here you have y and then y hat, right? So y is also a distribution. So if you think about it, the true label vector is also a distribution. But then it's kind of degenerate because all the probability mass is on the true label, correct? So this is also a probability distribution, right? So sums to 1. The terms are positive or non-negative, but then all the mass is on the true label. So the loss function here is something that compares to probability distributions, and the way it looks is sigma. So you have C components, right? So you go from I equal to 1 to C minus P log P there. That was entropy. This is minus the true one, the true probability distribution, minus the predicted probability distribution. Okay, so minus log of y hat I. Okay. Now, if your labels are like this, right? One hot vectors, this will simplify to something. What will this simplify to?
Negative log y hat.
Correct, right? So negative log y hat of what?
L.
L, right? Okay, what is small l?
True label value.
Correct, right? Good. So where L is the index of the true label.
Sir, I have a doubt here.
Yeah.
When we differentiation of loss function with respect to y hat, Its value log x means 1 by x, right? 1 by yl.
So that's tricky, right? That's a good point. So this is tricky. You should not. It's not 1 by yl. If you are trying to differentiate this with respect to, so this is a vector, right? Yl is y hat is a vector.
Yes.
You're trying to differentiate minus log yl hat with respect to, say, one of the components of the vector. It's not just minus 1 by y hat into whatever, right? So it's a bit tricky. We will not discuss this now, but it's a very good point. So it's a dangerous one. So we will avoid it. We will avoid computing this derivative directly. Okay.
Sometimes it is minus yi by yl hat. Sometimes y hat minus yl.
Yeah. So that's it's a bit tricky. So let's ignore that part for now. We'll do it in a roundabout way.
Okay. Sir.
Where L is the index of the true label. So does everyone follow this part? This is a very, very important function. Okay, this comes up in not just deep learning. This is the go-to function in LLMs. You are going to use cross entropy to train even large language models. Okay, so this will keep coming repeatedly.
Sir, this YL hat or Y hat L, how will you pronounce it? Y hat?
Either way is fine. YL hat, Y hat L.
So that is what we get from as the output of the last neuron. Output neuron.
Correct. Yeah. This is the okay. So this is the output of, yeah. This is Y hat 1. This is Y hat 2. So if the true label is 2, then this is Y hat 2.
Y hat 2. Okay.
Y hat 2.
According to the number of classes, this L will come.
Correct. Yeah. So for instance,
actually you have told that there are C classes.
Right.
Should we see?
No, this will be the true. So, see, for instance, for example, if let the true label be the second class, right? So you'll represent this as this vector.
Okay.
And the predicted and the output of the network. Output of the network is, let's say, 0.2, 0.4. 0.4, okay, or maybe I'll keep this different. So this is 0.5, 0.3, right? This is the output of the network. Then the loss function is negative log of. So when we say log, it's always log to the base e. So this is log to the base e of the predicted probability, okay, of the true label. So in this case, true label is 2. So this will be y hat 2. So this will evaluate to minus log to the base e of 0.5. Okay, that will be the loss function's value here.
You told me that predicted label means the prediction is this 0.2, 0.5, 0.3 only, isn't it?
Correct.
And that second one has higher mass there, 0.5.
Yes, that is right. No, it doesn't have higher loss. It has, so in fact, it has this particular loss value. So whether it's high or low, we'll come to that later. But for this example, so in fact, when will this loss be higher? Higher the value of, see.
Loss will be higher when that second one is low.
No, second one is high, right? Because, see, as, so
we have to subtract it from that other vector, isn't it? That 0, 1, 0.
No, we don't. So we are not subtracting, right? So what are we doing? See, as y hat L, right? So let's look at y hat L. As y hat L increases, just so if y hat L increases, or I'll just call this, if y hat L increases, what will happen to log y hat L? Will that increase or decrease?
Decrease.
This will increase, right?
Sorry?
And the negative of this will decrease, right?
We are taking simple log of the y hat.
Correct, simple log. So the
simple log of that value you are telling.
Yeah.
Okay.
Right. So what we desire is, if my true. So what do I desire? So my predicted probability should be close to 1. That's what I desire, right? For the true label. So the higher this is, so higher this is, the smaller the loss.
And my negative log will be low.
Yeah. Okay. So also note that negative log of y hat L is always a so what should I add here? Is it less than or equal to 0? Is this greater than or equal to 0?
Negative should be normally less than 0, isn't it?
Okay.
Greater than or equal to 0.
It's always greater than or equal to 0.
Greater than, yeah.
Okay, so
Negative should be greater.
Yeah, so point being
Okay. Loss should be low, so it should be greater. Okay.
Yeah, so always non-negative, right? So which is why we minimize this, right? So the loss should always be non-negative, and minimizing it should make sense, right? So okay, so that is cross entropy. So we have looked at the loss function, but what we have not looked at is the activation function, right? So that is the next thing. So what is the at the output should have the following property. What it should do is, let's copy this. Now I have, let's say, 3 classes, right? As we were discussing. So this has maybe 4 inputs in the previous penultimate layer. I'm not going to draw these weights. There are too many of them. I don't have the bandwidth for that. So I am going to assume that you can visualize the weights crossing here. So your y hat or HL is the output here. Now there should be something that converts AL into HL, okay, in a way that turns HL into a probability distribution. Okay, so I need something that will, I need some G of AL. So G of AL will give me HL, that is clear. But then it should have the property that HL is a probability distribution, or the sum of the components of HL sums to 1. Okay, so that's such a function exists, and it's called the softmax function. We have seen this already. So HL I, okay, here I means component. So this is for instance HL1. This thing will be HL1. Okay, this will be HL3, like that. So on and so forth. So HLI is what? It is e power H. A L I by summation, but I'll just write it down as AL1 plus dot plus e power C. Okay, so this is okay. I'll just do it for this example.
3 AL3.
Yeah, that's easier. So e power AL2 and e power A. Okay, so is this fine? This is called the softmax function. So this is going to have the nice property that HLI, if you sum this, is going to be 1. Okay, there's nothing but y hat I, the ith probability. Okay, so probability for the ith class is given by e power ALI by, so summation e power ALI. Okay, is that fine with everyone?
Yes, sir.
Okay, so that is the forward pass. Okay, so much time for forward pass. Yeah, so I hope the forward pass is clear. So now we can summarize the whole thing. So we can write the forward pass equations. It should be. So what are they? So first step is you set H naught to be this colon equal to means I am assigning H naught as X. step 1. Okay. Then what you do, then it's actually a for loop where you start with A. First you compute the pre-activations. So AI, assuming you have hi minus 1 in place, that will be Wi hi minus 1 plus Bi. Okay. So that is the pre-activation. And then the activation, that is nothing but G. I'm going to call this Gi because there is G is the same for all hidden layers, but output layer alone is different. So I just call it Gi of AI. Okay. So that is
this G of this G is that 3 functions, no? That
yeah,
Planet or Relu or anything.
Correct. One of those 3 functions. Yeah.
One of them. Okay.
Okay. So this is for, this will go for how many iterations?
L.
-1, no? This will be.
So 1 to L. Is that correct? So,
Oh, sorry. Yeah.
right. So for I equal to 1, so let's just work it out. For I equal to 1, this will be W1 H naught, which is W1X plus B1. It has to go all the way till the output layer also. So the output layer is going to give you AL and HL. So HL will be GL of AL. So GL alone will be different from the other fellows, and the pseudocode would have looked much better. But anyway, so this is a function. Let's call it forward. That will take X alone as input. Okay, so and then it has to output something. So what will it return? It will return. It should return y hat. But then internally, what we can do outside the for loop is you can set y hat to be HL. Okay. Again, you assign this as HL, and then you return y hat. Is this clear to everyone? This is the forward pass.
Yes, sir.
Okay.
So one query over here. GI, the output, in case of output layer, the G will be different. Na? So we cannot generalize it as GI, right? It will be some other G, right?
Yeah. So that's why I've called it GI. So outside the function, you can specify this, right? So GI of X or Z is equal to let's say 1 by 1 plus
Okay.
E1, something like this, right? For 1 less than 1, y less than n.
Yeah.
Right? Just for completeness, this will be okay. So I can't write it.
Yeah.
Okay, I
Right,
can't.
I understood.
Right. So,
Yeah.
but you can do.
Yeah.
Okay, so that's the forward pass. So forward of X will return y hat. So this is a function, typical function X. Okay, right. So at some point, maybe you can have a separate function which will take y and y hat as input. Okay, and it will return the loss, right? So let's say we are this. I'm not doing it separately, right? It's simple. So, but then this together with the loss function computation is the forward pass. Okay. So that completes the forward pass. Now backward pass is the big thing. So okay, so what is this backward pass? What really happens in the backward pass?
Good.
Computing gradients.
Yeah. So see, what is the goal? The goal is to find weights, to find parameters that will do something to something. So what are the parameters? Weights and bias.
That will decrease the loss.
Correct, right? That will minimize the loss. Okay, so we want parameters that will on a given data set. Okay, actually it's slightly different. It's not really correct. So you have training, testing, test data set. So there is the issue of generalization and all that. overfitting, underfitting. But for now, let's just say you have some data set on which you want to minimize the loss. Okay, so that's the goal, right? So you have to turn the knobs. You can think of this whole idea as turning or tuning your knobs. Okay, these parameters are knobs, and getting a configuration that will give you the smallest loss, right? This is similar to tuning a radio, right? So you have only one dial in a radio. For those of you who know what a radio is, right? So you have to tune into a particular station, and the closer you get to the station, the clearer the sound will become, right? So there's only one parameter to tune or one knob to tune. But in a neural network, you have huge, right? So millions of parameters sometimes. Modern networks like large language models, right? That power LLMs, they have billions, maybe trillions of parameters, right? So how do you tune so many parameters? The answer is there is a way, and that's gradient descent, right? So this you already know. So it's an iterative process, meaning in each iteration you adjust the weights. So in each iteration you nudge the weights such that the loss decreases, right? So for that, what do you need? You need the gradient. Okay, so if you want to nudge the weights so that the loss decreases, you have to do that in the opposite direction of you have to move in the opposite direction of the gradient. Okay, for that you first need to compute the gradient. So, and that is really difficult in a neural network at the outset because of the nonlinear nature of the input-output relationship, right? So it's kind of it looks very chaotic, right? So, and that's where you have this algorithm called backpropagation, which is an algorithm to compute the gradients of the loss function with respect to the parameters, meaning weights and bias. Okay, so that's the whole, that's what we are going to look at. Okay, so sometimes this is used interchangeably with gradient descent itself, but it is not the case. So what we mean by backpropagation is an iterative algorithm. This is also iterative, so meaning it will proceed step by step. That will compute the gradients. So what are the gradients? The gradients are typically you call it. So you have y comma y hat. That is your loss function, right? So you have y comma y hat. And this is the gradient of the loss with respect to W, gradient of the loss with respect to B, right? So you have.
Sir, why we compute gradients? What's the purpose?
So that you can use them in gradient descent, right?
Okay.
So see, the idea is, what is the idea? The idea
to
is
reduce the loss, right?
Yeah, you want to reduce the loss. You want to minimize the loss. Now, how do you minimize the loss? You have you can't. So in general, how do you solve an optimization problem? Unconstrained problem. So if you have, say, f of x equal to x square minus 2, or say something like x cube minus 2x square plus 1. If you want to minimize f of x, what will you typically do? You'll do f prime of x equal to 0, right? And then you will try to find the solution. So this is possible for simple functions like this, okay, where a closed form solution exists, but in general it's hard. Okay, so if you have some monstrous looking function like, say, so x power sine x plus ln of x by some random function, right, x square plus 1. So if I give you some function like this, it may be hard to find a closed form solution, right? So what do? You typically start with x naught, and then you say, okay, how do I find xt plus 1? This is how I do that, right? So I start with xt, and then I find the derivative of f with respect to, it's like f prime of x, right? F prime of xt. Okay, I move in the opposite direction of this derivative. So I don't move a very large distance, but I move a fraction of the distance. Okay, because that's where this approximation holds. So if I keep doing this, then eventually I will converge to some local minimum. That's the idea, right? This is gradient descent. Now, when you have
Opposite direction means 180 degrees opposite to f of x.
correct, yeah. So the gradient is what? The gradient is the direction of steepest ascent, right? Meaning, if you move in the direction of the gradient, your function's value will increase the maximum. So, but what we want is the function's value should reduce, right? We are minimizing. Therefore, you need to descend. That's why it's called gradient descent. Okay.
Yes, sir.
Okay. So always keep the bigger picture in mind. You need gradients because you're trying to minimize, right? Using gradient descent. Okay. So now comes the hard part. So how do we find the gradients, right? So, and the idea is we use our good old chain rule. So where we break up the whole computation layer by layer. Okay. So what do we need? We need this image, first of all. Where is that image? Should be useful. So we'll okay, right? So yeah, so what do we need? We mainly need the following. We have the loss function and we have the parameter. So let's say this is Wi, right? So Wi is this weight matrix. So if I want a particular element in the weight matrix, how will I index this? If I want one element out of this weight matrix, I should use Wi jth row kth column if I want that element. I do this. Is that fine with everyone? This notation.
So I means ith layer.
Correct. I means the ith layer.
J means
the jth row kth column.
That is jth neuron in the
output layer
and kth neuron in the input layer.
Exactly. Yeah.
Okay, sir.
Okay. So we won't use this now, but I just want you to be aware that this is the notation. Okay, is this clear with everyone? This is a scalar, by the way. Wij is a single number. Loss is a single number. So what will the loss function take as input? It will take as input, strictly speaking, x, y hat, right? So you need to pass x, that will give you y hat, and then you will also have y. So if you pass all this, you will get the loss, and then you also have the weights, right? Now, what does this represent? This is one element in the gradient, but intuitively, what is this?
Matrix.
Right. No, what I mean is, what does this quantity represent?
Change in
How
loss.
much?
Correct. Yeah, I think both of you are trying to say the same thing. So it represents the rate of change of the loss. Okay, with respect to Wij, right? Meaning, if
So this is the gradient of the loss with respect to weight, right?
Yeah, this is one element of the gradient. So, but yeah. So if I change or if I perturb, right? That's probably a better word. If I perturb, meaning if I nudge or slightly change the value of one of the weights, what effect does it have on the loss function's value? Okay, keeping, so this is important. Okay, this is the meaning of this quantity here. Is this clear to everyone? if I make a small change to this weight, one of these connections, what happens to the loss function? Does it increase? Does it decrease? Not just that, how much does it increase? How much does it decrease? Okay, so approximately, let's say I change the loss by 0.01. Okay, and I observe that my loss function changes by 10. Then this is what this quantity is capturing. Okay, this is a bad change, right? So if I increase W by 0.01, the loss is blowing up. So this is bad for me. Maybe for some other weight connection, this may be minus 100. This is good for me, right? Because this weight, if I increase the weight by 0.01, the loss decreases and it decreases faster. Okay, so this is a good weight for me. Okay, is this idea clear what we are trying to do?
Yes, sir.
Okay, right. So now, okay, that is the overall idea. Now, how do you compute this? So we typically start at the output layer. Okay, so we start at the output layer. I'll do this for regression because it's easier to show you how it's done for regression. Remember that the loss is half into y minus y hat. Okay. Now, it's very easy to compute the derivative with respect to y hat, right? So remember that y hat is nothing but HL, right? So this was HL. Now, it's very easy to compute. Okay, so again, another notation that SAR follows, I'll also be following this. This is important to understand. What is this notation? This is when I say something like this. What is this? This is actually the gradient of the loss function okay, with respect to, this is what it means. This is the notation that you will have to remember. Okay, is this fine with everyone? Because this will be used left, right, center. If you don't understand this, it's going to be hard.
So, sir, can we say that this is gradient of loss function with respect to the weight?
Exactly. Yeah. Likewise, this will be the gradient of the loss function with respect to y hat. Okay.
Okay. Yeah.
So what is this? This will be nothing but, in fact, I'll always use y hat minus y. That's easier. You also please do that. It should always be y hat. It's also fine if you use y minus y hat, but y hat minus y is easier. So this will be what? Is this fine with everyone? The gradient in this case is just derivative. It's y hat minus y. Is this fine with everyone?
So why is it just y hat minus y?
Because this is just, I'm just taking the derivative with respect to y hat, right? So this is nothing but dl. In this case, it's just a function of y hat. So this is what I'm doing. And it is 2 into half into y hat minus y.
Yeah. Got it.
Okay.
Yeah.
Okay, so here is the interesting part. This can be interpreted as an error term. Okay. We did this in MLT also, so some of you might remember this. So y hat minus y is some kind of signed error. Signed error meaning sign is there. Okay, it's not just positive always. Okay. The smaller the magnitude of the error, better the prediction. Okay, so this is output layer. This is important. What are we doing now? We are doing back propagation. We start with the output layer. So just as forward pass started at the input layer, we have to now start at the output layer. Okay, is this clear to everyone? This interpretation of the gradient at the output layer as a loss, as an error term. I hope that's clear. Y hat minus y. Okay. Interestingly, so this is for regression. Okay, I'm not going to prove this. We can prove this later on. It's not very hard. For classification, the loss is the same. Okay, has the same form, the gradient. So if this is for classification, so this is minus log of y hat L, right? Now, the gradient in this case, so in this case, for regression, this quantity is it a scalar vector matrix? What is it? Scalar or vector or matrix? Matrix, right? Correct? This quantity is a matrix or vector.
Vector.
Okay, we are doing regression. So what is y?
This should be scalar, no?
Should be scalar.
Y is scalar.
Okay, right? So this is scalar, right? So please remember that. So this is scalar. For regression, this quantity is a scalar. I think in week 3 or week 2, some question was there, right? Whether this is possible or not.
Week 2 is this.
Yeah. So for classification, if you look at again this nabla of y hat, it's again y hat minus y. That's a very interesting result. So it's the same. Okay, so you don't even need to memorize in a sense. So it's same y hat minus y. However, this quantity is a what is it? Scalar vector.
No, it's vector.
Vector. Okay, so please focus on the shapes and the kind of objects. That is the only thing that's going to help you remember these equations, because there are too many equations put together, right? Forward and backward. So a guiding light is what object are you dealing with? Here you are dealing with a vector. So y is a vector. So recall that y is a one-hot vector and y hat is a vector of. Okay, never forget that. So for classification, and fortunately the form is the same, only the type of objects are different. Okay, also remember that the gradient of the loss with respect to a vector is a vector. Okay, likewise, if instead of a vector, if it is a matrix, then the gradient will also be a matrix. Okay, so far is it clear? The gradient at the output. Okay, so now is where the game begins, right? The real game begins. So this is where things get slightly tricky, but it's actually not so hard. This is the yeah. So we'll be completely focusing on just one layer. So I just wonder if I need to. I just need this. I don't need the whole thing. So I don't need the whole thing. I just need. Okay, can you just give me 1 minute? I just need a proper diagram. So let's go here and fetch that diagram. I need only 2 layers. And let's say this is better. So what I'm trying to do is I don't need these edge weights to be so. I just need you to understand that there are some connections. More than that, I don't need that. Okay, so we'll be using 1, 2, 3, 4. Okay, 1, 2, 3, 4. 1, 2, 3, 4 is maybe too confusing. Let's make this 3. Okay, so or something like this. It will become clear what we are trying to do. So let's take copy this and move over to this. Okay. Yeah, so this is where we are. We are now at okay, right? So what have we computed? We have computed hey, wait a second. So this is y hat. In fact, I made a mistake. This is not y hat. This is wrong. This is actually here. Okay, so yeah, so I made a mistake here. This is actually not y hat. Okay, this was what I was pointing to earlier. This y hat is a problem. This is actually the gradient with respect to the pre-activations at the output layer. I'm sorry. Please make that correction. So in fact, this is actually equal to what? AL for a regression problem. AL is equal to, see, y hat is always equal to HL anyway. For any neural network, that is true. But for a regression problem, this is also equal to
AL.
AL, right? So this can actually be written as the gradient with respect to AL. Okay. And it's better to look at it this way. This will become, I don't have time to explain that part, but okay, so I made some changes, last minute changes. So is this might have confused some of you. So is this clear to everyone, what I have just done here? Anyone who is not clear with this?
You are telling now that output is AL for the last layer, isn't it?
Yeah, for regression, output is
Regression,
HL.
yes. So there is no function of G of AL.
Correct.
HL
Yeah.
is,
Yeah.
right, directly this AL is out getting out as output because
Correct.
it is regression.
Sir, here delta AL means derivative of loss with respect to AL.
Correct. Correct. Yeah.
Okay.
But this AL will also be having that some terms, etc., isn't it? Of all the weights and bias of the previous layer.
Yeah. Yeah. That is true. So it'll have the it'll have this these three into W plus B. That will be there. So that is how AL would have come about. So this is regression. I hope we are looking at regression, right, in this example. Yeah. So G of Z is Z, right? So therefore G of AL
it is AL.
Equal to AL. And that is what we call HL.
Okay. Even if it is a function, we call it HL only, isn't it? Y hat.
Yeah, we call it y hat. Yeah.
Oh, yeah.
Okay, so I hope that is fine with everyone. This is so I'm calling this AL, and for classification also, this AL gradient with respect to AL turns out to be y hat minus y. Okay, is this fine with everyone? Can I go ahead? Okay, right. So now we come to we assume, right? So now this is where the iterative process comes into picture. We assume that we already have the gradient of AI with us. Okay, so and now the task is to compute what all can we compute. So you'll see that we can actually compute hi minus 1 with this. We can also compute wi with this, and finally we can compute bi with this. Okay, and one more which is so all these we can compute. Okay, that's the beauty of the algorithm. So let me add as many annotations as possible. So this is layer I. Okay, this is layer I minus 1. Okay, what do you already have? Remember, you have already computed gradient AL. So it is reasonable to assume that you have AI with you. Okay, and AI will be coming from the right. Okay, it will be coming from the right. So gradient of AI is there with you. Now, in terms of this picture, what are these quantities? So you have AI minus 1 that will be sitting before this neuron. After activation, this would have become hi minus 1. Okay, that is what will go as input to this output neuron, right? So therefore, you will end up computing AI here. Okay, what this neuron will be producing as output is hi. Okay, what will help us produce this output is wi sitting here and bi sitting here. Okay, is the diagram clear so far? Okay, so now always,
This bias, bi is the bias for the outer layer.
yeah, these 4 values are put together in bi.
Okay, that means from the output we get that gradient. Gradient, isn't it? That AI means gradient, isn't it?
Yeah,
The
AI
difference
is
between the actual and the predicted.
so this is AI. So what is gradient AI? It is telling us how does the change in AI affect the loss function. Okay, so what is AI mean? It means the following, right? It means it's actually a vector first of all,
Okay.
where each term will be of this form, right? It will be how is the loss affected by the pre-activation value in one of these neurons, right? So this AI1,
Okay.
AI2.
Oh,
Right?
okay. So it will be also a vector of some
Yeah, it will be a vector having, in this case, 4 values.
4. Okay.
Okay, so that is what you have with you. So now what we are claiming is once you have this, you can compute this, can compute gradient with respect to this, and this. Okay. How will you do this? So the main point I'm going to focus on today is remembering this, right? So proving this is not too hard, but remembering this is a pain. It's not a pain. That's what I want to show you. For that, you have to first write down the forward pass, right? So what is the forward pass? AI is wi hi minus 1 plus bi. Okay, that is the main equation you have to look at. So this is forward pass, right? So recall. So you have this. Now what is there with you? You have AI with you. Okay. First thing is you need, let's start with the simplest. Okay. You need to find gradient with respect to bi. But you have AI already with you. So if you look at this equation, you notice that whatever is the gradient with respect to AI, the same thing is the gradient with respect to BA, again by chain rule, right? So very quickly, so this is what? This is with respect to L, right? So L is what you have. So dou L by dou AIK is what you know. But what you need is dou L by dou BI or BK, okay? BIK. That's what you need. So this is what first you make use of what you know. That is this, right? So dou L by dou IK, and you multiply that with dou AIK by dou BIK, right? So uh, if you do this element wise, you will notice that these are one and the same because these are constants, right? Remember what partial derivative is telling you. You have to keep everything else constant. So BI is the only variable here. So the gradient or the derivative of one component of AI with respect to corresponding component of BA is nothing but 1. Correct? So for a moment, think of this as scalars. This is some WH plus B. And what I'm asking you is, what is dA by dB? What is dA by dB?
It's 1.
It's 1, right? So think of them as, so dou A by dou B, I'll put it this way, right? So you are keeping W and H fixed, you're only changing B. This is 1, okay? Very similar thing is happening here. I'll delete this, you only need this. So is this fine with all? Gradient of BA is just gradient of AI. Okay. So if you are going to, if you think you are going to forget this in the exam or in other, wherever else you are going to apply this, what should save you is shapes of the gradients or objects involved. Okay. So this is the, at least as far as I am concerned, this is the only way I managed to remember this properly. What is the shape of AI? Or what is the shape of gradient of AI? Ni, comma, right?
Yeah.
Okay, so let's make this very explicit. This is going to be Ni. Okay. DA is what shape? Same shape. Okay. So you just equate them. Okay, it's a very crude way, but it's not wrong. Okay, you are just trying to remember. So whatever gradient here, it just passes on to B. So I'll keep noting down the shapes here and the equations here. Okay, so that you see the clear parallel between them. So this is BI. And notice that from the forward, so everything is there here. The forward pass equation gives you all the information that you need. Okay, next we come to WI. Okay, so what do we need? I need a formula for. Okay, so what do you think the shape of gradient of WI is going to be? What should be the shape of the gradient with respect to WI?
I cross I minus 1, is it?
Yeah, so it's Ni. So it's the same as the shape of Ni is Wi itself, right? So the gradient is going to have the same shape as the matrix, corresponding matrix. Okay, is this fine with everyone? The shape? Because if it's not clear, then this you won't understand the equation for this one. Okay. So now we come to this. Okay. Again, I'll maybe in some other session I'll tell you how to derive this. It's very simple, but for now let's just look at trying to remember this using shapes. So how will I remember this? I need something of shape Ni cross Ni minus 1. Okay. So what do I have in place? I already know AI. So that is the information coming to me from the right. That is gradient of AI. And notice that gradient of AI is giving me shape Ni. Okay. So that should be on the left. Okay. It's a matrix. Think of this as a Ni cross 1 matrix. Okay. That is what I have. Now, if I want Ni cross Ni minus 1, I have to multiply this with the matrix of shape 1 cross Ni minus 1. Is that correct? If I want to get gradient with respect to W, if I want the shape, finally the shape is Ni comma Ni minus 1. Okay. So if I want, this is what I already have. And if I want to produce Ni cross Ni minus 1, I have to multiply that with 1 cross Ni minus 1. Where do I get that? Again, forward pass. So one influence is AI. The other influence for Wi is Hi minus 1. Okay. So if I multiply by Hi minus 1, the shapes are not going to be compatible because, let me remind you that Hi minus 1 is what shape? ni minus 1, right? So what should I multiply this with?
Transpose of hi minus 1.
Transpose, right? So this is actually called an outer product. For those of you who remember, we did this in MLT. So XX transpose, right? For the covariance matrix, if you remember, this is what we did. So 1 by n c equal to x. We did this for MLT, right? So this is a vector into vector transpose. Something similar is happening. So this is called an outer product. So outer product. That is what is happening here. So one vector is of shape ni cross 1, which is gradient of ai. Another one is of shape 1 cross ni minus 1. So if you multiply them, you will end up with the desired shape of your weight matrix. Is this fine with everyone? This is how you remember this using just the shapes. Okay, so that is wi. Using a similar argument, what is remaining? Hi minus 1 is there, right? So what is nabla of hi minus 1? So again, go back to the shapes here. So what do I care about? Hi minus 1. This is going to be of shape ni minus 1, comma, right? Once again, what is already available to you? Gradient of ai is available to you, right? So you start with that. That is going to give you, so that is already giving you ni comma 1. Okay, there is another influence waiting here, which is wi. So another influence is wi, right? So that is ni comma ni minus 1. Okay. So I have to somehow multiply these two quantities to get ni minus 1 comma 1. That's what I want. So how should I multiply this and wi so as to get ni minus 1 comma 1?
Wi transpose gradient of ai.
Correct, right? So you have to multiply wi transpose with this fellow. Does everyone get this part? wi transpose will be of what shape? It will be of shape ni minus 1 comma ni, right? You reverse it. And then if you multiply this with ni, you will end up with ni minus 1 comma 1, which is what you want. Okay, is this fine with everyone? Okay, so I know I am not giving you the exact intuition. It's actually quite interesting how these things come about. What I want you to mainly take away is, if you know the gradient with respect to a, and you are trying to find out, let's say, the gradient with respect to w, two factors are involved. One is a itself, and the other factor is h. Now, if you flip it, right, if you want the gradient with respect to h, then you have two other factors, which is a and w. Okay, so if you focus on this, the other two are important. If you focus on this, then a and h are important. That's what you will see here. So if you want w, a, h, then wa, right? But the gradient of a will always be there, because that's where it comes from. Everything comes from that. Okay, so what is the final thing that is pending? This fellow, right? If you have this fellow, you can repeat the process, right? So notice that you started with ai. If you want this process to be iterative in nature, what you need is ai minus 1. Okay, so that will kind of complete the whole thing, because now you can run this in a loop. So how do you get that? You notice that you already know what hi minus 1 is. You have hi minus 1 with you here, so that's good for you. So what is hi minus 1 in terms of the forward pass?
It's the activation function of ai minus 1.
Yeah, it is g of ai minus 1. Okay, so that is hi minus 1. So if I want the derivative of or the gradient with respect to ai minus 1, then I just need to by chain rule, the gradient of G will come in somewhere. Okay, so this is nothing but whatever gradient you already have. Okay, this is what is called an element-wise product, right? So this is not too hard, but so I'll just tell you what this means. So for instance, if AI or HI minus 1, right? So if is equal to say 1 comma 2 comma 3, okay, and G prime of, this is the derivative, right? So G prime of AI minus 1 is, let's say 0.13, 0.2, whatever, right? Now gradient of AI minus 1 will be the element wise product of these two. So if you want A minus 1, what you have to do is you have to do 1 into 0.1 comma 2 into 3 into 0.2. Okay, that's what this means. This O dot, this is called as, sometimes it's called Hadamard product, right? So your libraries like NumPy, if you try to multiply two NumPy arrays like this x into y, that's what it will give you. It will give you this element-wise product. Okay. Yeah. So is this clear to everyone? These are the backward pass equations. Now we just run it in a loop. So for I equal to L dot 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 all the way till I equal to, what should I stop with? Where will I stop? What is the final thing that I want? Gradient of?
Before the input layer.
Correct. So should it be 1 or 2?
1, I think. 1. A1, isn't it?
0.
It won't be 0 because there is no H minus 1, right? So you want till W1, right? So see, these are all actually things that are redundant, like what do you call collateral damage, right? In some sense, this HI, AI and all you don't need. What you really care about is only WI, BI. Okay, so this is what this looks like. This is backward. Now backward will take a whole host of things as input. I'm just adding dot 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 for now. First thing you will compute is this one, A capital L. And what is this? You must remember this part. What did we compute this to be? For both regression and classification, this turns out to be?
Y hat minus y.
Yeah, y hat minus y. Okay. So once you have AL, I can start. Okay. So BL will be just AL. WL will just be AL into HL minus 1 transpose. And then I can go to the previous layer, right? So HL minus 1. Once I have HL minus 1, I can go back to AL minus 1. And then I can repeat the whole process. Okay. So this is, finally, you will return, what is important for you is you will return a big list containing W1 all the way till WL. And then you will also return B1 all the way till BL. Okay, so that's what you'll return, and then you'll do gradient descent, one step of gradient descent, and then you'll keep iterating. So that's a bigger iteration. But yeah, so this is just for completeness. This is y, this is y hat, sorry, hat y, and you also need the AIs, HIs, because you're going to use them, right? So you need these fellows. Okay, so is this at least somewhat clear? I don't know, I'm not sure if I was able to explain the backward pass well enough, but at least for you to remember them, it should be possible using this equation in conjunction with the shapes that you expect. You should be able to reproduce this. Okay, so any questions so far? It's the end of that is what I had to present today.
So can we think about this like in a way like we are just taking the partial derivatives and going on, and by the chain rule we are multiplying it with grad of a and like this.
Yeah, it's so back propagation is just chain rule applied. It's chain rule on steroids. Okay, so you are just doing chain rule, nothing else. The only thing is the reason it's called back propagation is because you start with grad AI here, and then it's like this nice algorithm allows you to end up with grad AI minus one. So in a sense, you have back propagated the gradients, right? So this is the entirety of back prop, right? So once you know grad AI, based on how the layer is structured, you can pass on the information to grad AI minus one. See, what are you passing on? So why is it called propagation? So you are actually propagating information from the output layer to the input layer, right? So remember that this whole error term, right? So this is what you had. So this is the error that is, in some sense, is the error that is involved uh, at the output layer, right? And you start with that, and then you keep propagating that backward all the way to the input. Okay, using the chain rule. So you make use of the chain rule. So grad W is going to be grad A into grad H, right? Of course. So, sorry, grad A into H. But then the shapes matter. So I'll repeat this. So grad W is going to be what? Grad A into H.
So you're not audible.
Hey, I'm sorry. Where did you lose me? What was I saying? Can you hear me?
Yes, sir.
Yeah, sorry. What was I saying? Like, was it the full?
Y- You were showing the back propagation, like how do we go from the.
Okay. This part while drawing this, it was there, right?
Yeah,
Connection.
yeah, yeah.
Okay, okay. So that's what I was, I think, saying. Yeah. So, yeah. How do you remember this? It's yeah, same thing. So you
What
start with
is
grad
meant
A.
by propagation? You are telling.
Yeah, yeah, yeah. So you start with grad AI, and that is uh, yeah. So one way is to treat them as scalars, right? So if you are to differentiate A with respect to H, what would you do? You will, sorry, if you are to differentiate L with respect to H, you would first differentiate it with respect to A, and then multiply with W, right? That's exactly what you're doing. So you first differentiate it with respect to A, and then multiply with respect to W, right? So multiply with W. The shapes alone, you'll have to, only thing you have to take care is shapes. So wherever there's a transpose, you'll have to add it in the chalk, right? So few things you'll have to take care. The rest of it is not too hard. So if you want to understand it deeper, it is not too hard. Mm, but maybe you can do it if you're interested, right? So not now, but some other time. It's not very hard to see why beyond shapes, right? So you can ask the question, why should it be exactly this form? Why should it be grad A into H transpose? Not very hard, but we can maybe do it some other day. So, but is this convincing enough for all of you? Backward, the way we have put it down.
Yes, sir.
Okay, right. Yes, yeah. That is all I had. So what should you? Some extra points that you can maybe Google and find out, right? So this was popularized in 1986 by Rumelhart and Hinton, right? So Hinton subsequently went on to win Turing Award for computer science and the Nobel Prize in physics, right? So last year, okay, this happened last year. So that is they popularized the back propagation algorithm, right? So even to this date, networks, no matter what kind of neural networks they are trained by back propagation. But you have to note that implementation is not quite the same as what you see here. So they don't actually, uh, they're not necessarily going to use the same equations. What they're going to do is they end up doing what is called automatic differentiation, right? So you can search for this. It uses this concept called a computational graph. Okay, some of you might find this easier to understand than these equations. So it uses a computational graph. It's actually a graph, right? So it's a graph structure that they form, and so that is how they do it. So back propagation, even though it was available way back in 1980s, right? So they had discovered it during that time. Somehow they were not able to train neural networks on a large data set. So it all had to wait until 2012. Okay, so 2012 is when the three things happened, right? You had large quantities of data, you had hardware in the form of what are called general purpose GPUs, right? So graphic processing units that are now used not just for rendering graphics, but for doing computations, right? So you had hardware and you had smart algorithms. I just call that software. So one big component is this ReLU. Okay, so you will see ReLU in more detail. Small changes to the software or the algorithms, right? And ReLU was one of them. So replacing sigmoid. So we were looking at three functions, right? What were the three? So sigmoid was probably the dominant function at that time, but then when they made this small shift to ReLU, that greatly changed things. Okay, so these three together kind of made training new networks using backpropagation possible. Okay, so anything else? Any other questions? If not, we will.
So can you share this notes to these?
Yeah, I can share, but it's kind of all. It won't make sense without the live session. Okay, so I can share, but you'll have to refer back to the session so that it makes more sense. Okay. Yeah. So see, next week, week 4 and week 5, I don't know if we really need to meet on Mondays because week 4 is just optimizers, and maybe we'll quickly meet for maybe half an hour alone. I'll tell you what algorithms you need to really focus on. So you don't need to know. Of course, please watch the lectures, but when it comes to optimizers, uh, we are mainly focused on the following, right? So you need to know what is gradient descent. You need to know batch GD and SGD, right? So these two you need to know, and then you need to know momentum. So that is that. Nestrov accelerated gradient descent, that is also there. So you kind of know these two, and then there's RMS prop, which will come in week 5. Okay, and Adam. Okay, these are sort of the main optimizers you need to know. Prof actually goes on and covers so many other optimizers also. So he covers many variants of this, right? He covers Adagrad, he covers NADAM. So all those things are there. But from if you are only looking at the exam point of view, that plus what is really happening in the industry, right? Usually we end up using Adam or maybe even plain batch gradient descent, right? Most of the time. So these turn out to be the most important algorithms from both from a practice point of view and exam point of view, right? So week 4 and 5, what I'm trying to say is not that dense. Okay. Yeah. So that's all I had. We'll meet
Sir,
again. Yeah.
For quiz 1, week 1 to week 4, right?
Quiz 1 is week 1 to week 4. Yeah.
Week 1, yeah, only introduction, right?
Week 1, that perceptron is there, right? Perceptron.
Okay.
So the history of deep learning has gone out, so that is not there.
Okay.
But we will still have, what is that? Perceptron learning algorithms.
MP neurons.
Yeah, MP neurons. Yeah, sorry. Yeah, that is important, right? The MP neuron. So all that is there. Excitatory inputs, inhibitory inputs, all that. So that whole MP
So
neuron.
no need to remember history, sir.
For the exam, no need, but it is important to know the history, right? So if you want to get an idea of where the field has, how long the field has, or where did it originate and all those things, right? So for that you need to know, but for exam you don't need to know.
Okay, sir. Thank you, sir.
So what was the tool that you were using to put up the graphs for deep learning those neurons?
For creating you mean this one?
Those neurons, the graph.
This one, you're saying?
Yeah.
This is called, so this is Alex Nail. So that is the URL. You can maybe share it here. So.
Okay. Okay, thank you, sir.
All right. Okay. Yeah. So we stop sharing. Sorry, stop recording, streaming, and we can meet again next week. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Yeah. Thanks.
Thank you, sir.
So will we be doing any example of this next